Hello students. So we are in chapter 3 and we are almost done with chapter 3, okay? And today we will actually before chapter 2 I wanted to do chapter 3 so that you can understand basically so what is the motivation. So in chapter 3 we have started with transfer function, and just explaining the transfer function we studied about the electrical circuits and the electromechanical system, purely mechanical systems, so all those kind of things, and we learned from purely the transfer function point of view, okay? And in chapter 2 basically this is talking about the just block diagrams, you know. So let me little bit things are left in chapter 3, so I will finish that. After that we will do what is given in chapter 2, okay? So chapter 2 is basic things I already talked about and gave example. So instead of saying making a block diagram saying that this is a plant and this actuator, actually showed what actuator is. So that's why I wanted to do chapter 3 first and then chapter 2, okay? Yesterday we studied the servo mechanism or servo control or motor control. Yeah, so there was a plant, I said, right? So you had a plant, and what was the plant for us was flywheel, right? So this is flywheel was the plant, okay? And then there was actuator. Yeah, so this is actuator, right? Okay, and actuator was for us, it was a motor, yeah. And then typically before that we have some control system, yeah. So control system. In yesterday's example we used K1 here. We just wrote K1, just one, we assume proportional control. Yeah, so you understand now when I say proportional control, because we have done the equivalent circuit. Like a spring is proportional control, like a input is output directly proportional to input, right? So this is proportional. So whatever is here, this multiplies by K1 becomes here, right? So this is how it is. Then this goes like this, and then there is a negative feedback. Yeah, so here there is a sensor, and there is a summing point here. So this is a minus, so this is a negative feedback. So this is plus, and this is the input. Right? So this is what we have studied, right? So these are typically what the control system looks like. There will be actuator which will be operating the plant, and there will be some output. From the output we are reading through the sensor, and which will have some transfer function. All of them will have some transfer function. This will have transfer function, this one, all of them will be transfer function. And here we are going to sum up, and accordingly how it works, right? You can also write here, let us say this signal is RS going into that, and going out is CS, like this. Yeah? So RS means this is input, this is input, and this is output, like that. Yeah. Okay. Now all of them will have some transfer function. So let us say this is the transfer function. Let's call it T1. This is or typically you also write in terms of G. You say G1, G2, like that. So let's call it T1. So here we have T2. Say this is T3, and here we have T4. So yeah, so all is as a function of complex frequencies. So this like that. Yeah. Okay. So what is the relation? Yeah. So yesterday also we did like that. So what you say, this will be a equivalent to minus plus. You have RS here, and then here we have G, S equal to T1 times T2 times T3. So this is we are, instead of having 3, we can combine them into only 1. So it will be like that, CS. And then we have here, which is T4 S, and then you have like this one. Yeah. So this is what it is. GS is nothing but the open loop transfer function, right? Transfer function, and we can do the analysis as you did yesterday. And so here, if you see here, this is the C coming here. This here, this becomes CS times T4, right? So the total becomes here the RS minus T4S times CS, right? So this is the error. You can call it, this one is E, that this is ES. So this is ES equal to this, yeah, okay. And then CS is GS times ES, where ES is equal to this. So GS times R minus T4 times C. Okay, so I'm not writing as a function of S here. And finally what you get, so this and this, so 1 plus T4, so 1 plus T4 CS will be equal to GS times RS. Okay, so CS over RS, CS over RS is, so let us see. So okay, GS is also there. Okay, just a minute. So CS multiplied by this is there. So 1, then plus T4 times GS is equal to RS times GS. Yeah, and hence you get, we can write it here. From here we can get the overall transfer function, that is CS over RS is equal to CS over RS equal to GS divided by 1 plus T4S times GS. Yeah. So this is what we call it, the closed loop transfer function, right? So GS is the open loop, which is simply T1 times T2 times T3, whatever there, till output. From the summing point till the output, whatever you have, you just multiply them, you get GS. This is open loop transfer function. And in order to know the closed loop transfer function, if you know GS, it will be GS divided by 1 plus T4S times GS. So whatever you have here, multiply by this, you get that. Okay. So this is the control system. What is the use of that? Why do you need that? And we have been talking about this control system can be proportional, or can be integral, or maybe derivative, and the combination of them. Yeah. So here, let us say we want to, so error, let us say we want to make error equal to 0, or that will only happen when RS equal to CS. Whatever you want, whatever you are giving here, the same thing is the output, right? So that is what that's called a steady state, right? So whatever is going here is going out, because in that case, I mean whatever giving here is not going out, but here the total sum is equal to 0. Okay, so this is ES. So total sum, meaning that total error, this is the error here, right? So total error you want to be 0. Yeah, so this is the ideal condition when that really means that there is no error, and hence the system will be maintaining the position. Yeah, so if you want RS ES equal to 0 or RS equal to whatever you get here, so this is the CS, here it will be CS only, here you get T4 TS divided by CS, that's what you get here, right? So RS equal to this one you want, right? Okay, so we have this closed loop system. Yeah, so what it says CS equal to this. So TS times CS becomes, okay, this is T4. This is T4. Yeah. Okay. Let us first write this one in terms of the T1, T2, T3, because we want to find out what kind of transfer function we need. So what we want to know is what is the motivation of this, what kind of function we need for this one. Yeah, so that the whatever we are doing will make sense, and hence I am doing that. Okay, so CS over RS, so CS will be equal to RS multiplied by, and then we have GS, where GS you have T1 S T2 S times T3 S divided by, you have 1 plus T1 S T2 S T3 S multiplied T4 S. So all of them multiplied here. Yeah. So this is what the equation is, right? Now we have to find out ES. Let us say you want to find out ES now. So ES will be equal to RS, right, minus T4 S multiplied by CS, right? So RS minus T4 S multiplied by CS, and multiplied by CS, CS is this one. So what we have? We have RS, okay, and then we have T1, T2, T3. So T1 S times T2 S plus T3 S, and T4 S is already here. Yeah, and we have divided by, yeah, so here we have divided by, all of them divided by, have 1 plus T1 S times T2 S T3 S times T4 S. Remember, our control system is T1, right? And let us say we want it to be 0, right? So that's what our goal is. Regardless of what the value of S is, we always want, we should be able to control, meaning that whatever value RS we give, our error, if we get 0, that really means it is at the right position. Yeah, that's what it means. Okay, now from here, if you make ES equal to 0, yeah, and then what is the meaning of that? Okay, so we I mean, ideally, like this ES or error should be 0. Yeah, but this is another matter, whether it's really possible or not. For example, in this case, if you make equal to 0, and then what happens? If this you multiply here, so that really means this multiplied by this one, so you get RS, right? Simply RS, and then you will have 1 plus T1 S, T2 S, T3 S, T4 S, and all equal to 0. By the way, here it should be multiplied, yeah, not plus. Yeah, so since RS is, this will be 0 only when you have RS equal to 0. That really means, right? So the whole thing, this is not equal to 0. I mean, it should not be equal to 0. Otherwise, we blow off somewhere like the closed loop, the transfer function. In that case, will be infinity, as you see here. So this plus this should not be 0, right? Okay, so that really means that in this case, this is possible only when RS equal to 0 or input signal is equal to 0. So that really means, that really tells you the steady state error is not equal to 0, right? So it tells you this is steady state error. So this is a steady state, so the steady state error not equal to 0. Okay, but in any case, what you have found out here is the error itself. So this is what the is the error, right? So this one is the error in this case. Okay. And this error only keep on multiplying, like so. Here ES is RS divided by 1 plus T1 times T2 T3 times T4. Here it will be T1 you multiply here it will be T2, here it will be T3. So this is how finally you get the final value here. You get RS times T1 times T2 times T3 divided by 1 over T1 times T2 times T3 times T4. Yeah. So basically, just for understanding, you see like how you can find out once you have all the transfer function, you can find out what is the value of the signal here, right? So here, what is the value here? Here, if it is ES, here it will be ES times. So here it will be ES times T1. Here it will be ES times T1 T2. Here it will be ES times T1 T2 T3, right? Which is equal to actually CS1, right? One thing also notice that here the T4, T1, which T1 corresponds to the control system transfer function, hence and you see T1 right here, right? So that means T1 plays a role, yeah. So that really means the error is going to depend on this also, right? Is going to depend on this. For actuator, you cannot do anything. Actuator, in most of the times, this is fixed only the kind of the transfer function it has. You have not much control. For example, a motor will have the kind of transfer function it has. It will have like that. Plant is given to you. So again, the transfer function is given. You have control over little bit on this sensor, different kind of sensor you can choose, but still you have some choices to make. Yeah, so to some extent you can change. You can also have some kind of extra transfer function added here that you can do. So T4 you can control a bit, but T1 you have lot of choice. So that means T1 you can use whatever you want, whatever is the best for the system to control. Controlling that really means that you should be able to get steady state error equal to 0. Basically, you should be minimize it. So in order to minimize it, the kind of system the kind of control system you need will be decided. Accordingly, you can find out basically, and which all options we have. So this can be a control system, could be simply just a gain only, right? So you call it proportional, right? So proportional. That means in this case, T1 will be just a K, right? Just a constant number. So proportional, it will be just a gain basically, just a gain. That's it, right? So let's say call it K1. Or this control system could be maybe instead of K, if you have a derivative, maybe derivative will help, and in that case gain will be something like say the transfer function, you say T1 equal to gain equal to K1. So in this case will be T1 is equal to K1 times S. So this will be derivative. As you know, when there is a derivative, like in that case, you have you multiplied by S, right? Then it could be PD. So that really means the proportional plus derivative. Okay. So maybe I write here like this one, K1, this is K2S, and in this case T1S may be something like K1 plus K2S. Yeah. Then it could be integral, right? I for integral. I. So integral. Okay, in this case could be T1S equal to maybe K3 divided by S. As you know, then it is integrated. Then if you take the Laplace transform, you have 1 over S. Yeah. Then this could have, say, P I, say, proportional integral plus integral, yeah, integral type. So in that case T1S you can have K1 plus K3 over S, yeah. Okay, then it could be PID, so that means proportional plus integral plus derivative, and in this case you have proportional term coming K plus integral term coming, then will be K3 over S, and then derivative term as well. So derivative term you have K2, so K2 times S. So what we see is there are a variety of kinds of control system we can use, and this is going to have effect on the error basically. That's why we have studied different kinds of control system here, starting with the proportional, then derivative, proportional plus derivative, integral, or proportional plus integral, or PID, proportional plus integral plus derivative. Yeah, there could be other kinds as well, but these are the ones which are used very frequently. Okay, so normally these are the ones which are used and which are easy to make also, as you have seen that you can use the op-amp basically to get any kind of transfer function, and hence we have studied op-amp so that any kind of transfer function we can make and we can have it here, and so that we can influence the working of this, or we can have the more control, so that our the error, whatever we want to minimize it. Means we want to have CS, we want to have a control over CS by varying control over CS by this control system. And how we do it? That really means this is the required position, yeah, RS, and this automatic control system will work such a way it will achieve CS will be close to RS. That's what it means. So look at table 3.1 of your textbook, and there you have the list of variety of transfer functions that you can make using op-amp. Right? So this kind of, if you want PID, for example, control using op-amps, you can actually have a circuits as given in table 3.1, and similarly for this and all. Yeah. So this, although the working principle we have studied already, so you know that if you have a connection like this one, right? You remember? So this is Z1, right? And here this is Z2, like this one, right? And hence the output over input. So this is say EOS, this is EIS, and EOS over EIS is given by minus G2 over G1, where these are the impedance. Yeah, so minus like this one. Hence, there will be two of them. Yeah, so just using this one and using some resistance and the capacitor only, where if the resistance is there, then you have just R. Otherwise, for C, you have to take 1 over C times S. Yeah, so that will be the equivalent of the impedance. Accordingly, if the series, then you have to R plus 1 over CS. If parallel, accordingly you have to do, and this works like that. So please see this table, and you will automatically understand how the different kind of controller you can make by choosing different impedance, you know. So and you can make it. Yeah. So I may ask some questions from that table also, right? So there may be something like maybe give some values and say that will make what kind of control system, whether PID or PI, PD or like that. So we are now done with chapter 3. Okay, so in chapter 1 we will look at the block diagrams only, the how to actually the simplify the block diagram. So here we have done one simplification. Say we have 3 T1, T2, T2, T3. We multiply them together. We made only one. But here the flow is quite simple. It's possible that the flow is quite complex. In that case, how to solve that? Yeah. So I will actually solve a problem from chapter 1. So you will understand now the problems of chapter chapter 2, because chapter 2 is very simple basically. So in chapter 3, I also actually taught chapter 2 also, you know, so that you can understand that. So only thing is chapter 2 without actually explaining, showing what the plant is, for example, it is talking about plant. So that's why I did not follow that pattern. I first taught in chapter 3, or automatically chapter 2 is included there. So now you have to do problems from chapter 2 also, chapter 3 also. So chapter 2 problems you can understand now, and you will be able to do it. Okay. So I'm going to solve one problem from chapter 2. So you will understand that if it is a complicated workflow diagram, if it is the control flow diagram, if you have, then how to solve it if you want to. Yeah. I'm going to solve a question number B to 1. Yeah. So B to 1. Okay. So this will also be a tutorial problem. I will post the list of tutorial problem as well. So here it says find out the closed loop transfer function for the diagram is given, and this is like this. So this is a plus, this is minus, and then you have RS here like this, and then from here it goes out, and then we have G1 given here, and G2 here, Z2, and then adding here plus both, so it comes like this. Yeah, and then goes like this one. So this is CS. Yeah, and coming like this one, and here Okay. So G3 here, this is G4. Sorry, this goes like this. Again is adder. So like this, this is plus, this is minus, and goes here and goes minus here like this. So this is, as you see, this is a complex, more complex than what we have studied. So in that case, if if you want to know closed loop transfer function, so closed loop transfer function means CS divided by RS equal to what? It says simplify the block diagram. So this is a block diagram. First simplify, and second is find this one. Yeah, the closed loop. It says closed loop. Closed loop means whatever you are seeing that you have to find out. Yeah. Okay. Now how to simplify? Okay. So this is question number 321. I may ask in the continuous evaluation, the assignments, or in quiz. So how to go about it? So first I would write here ES. Okay, so this is the error. ES. Okay, and here we have CS. Of course, this is both CS only. So that means here also we have ES. Here also we have ES. So you can write like this one. And here you have G1 times ES. So G1 times ES, and you have added here. So this becomes CS is nothing but equal to this is G2, right? So it will be G1 plus G2 times S, right? So simplification, when you say simplification, that really means what? So basically CS is equal to G1, you are adding, right? So G1 plus G2 times ES. So both of them combined, you can combine it into a single one. So this becomes G1 plus G2 simply, right? So this is what the simplification means. So this is simplification. Yeah? Okay, so this is done. Similarly, if you see here, this is plus, this is minus. So accordingly, you have to do. So this is the here. This is plus, this is minus, hence this will be G3 minus G4 here. Yeah? So you can write this way, or you can write this also. So this is CS, this is also CS, this is CS. Okay, this one is G4 times CS. This becomes G3 times CS. G3 times CS, and plus and minus. So here what this minus this. So what you get is here you get G3 minus G3 minus G4 times CS. That means CS is coming here, and finally you have G3 minus G4 times CS. Hence this has to be G3 minus G4, right? And hence this is how it is going like this. And then you have here minus, and then this is plus here. So here this is RS, this is CS, and then this is getting like this one. Yeah. Okay. So now the CS over RS, you can write very easily. You can have this equal to CS over RS equal to simply will be equal to the open loop transfer function, which is G1 plus G2. This is open loop transfer function, right? Open loop transfer function. And this is, as you know, plus, and then you have whatever you get here will be here, G3 minus G4, and multiplied by same again. So G1 plus G2 will be the answer. Yeah, and how I know the answer? We have done already, right? So you can have, so this is CS, this is CS, here you have G3 minus G4 times CS. So here, this value, we have RS minus, and then you have this G3 minus G4 times C times S, right? Okay, so RS G3 minus G4 times CS is this one, RS minus this, and multiplied by this has to be CS. So it has to be CS equal to G1 plus G2 multiplied by this RS R minus G3 minus G4 times CS. Yeah. Okay. So if you simplify, you will get that, right? So if you simplify, you will get CS multiplied by 1 plus G1 plus G2 multiplied by G3 minus G4, right? So CS 1 plus G1 plus G2, G3 minus G4 will be equal to RS times G1 plus G2. Hence this. Or you can simply write, if you know the open loop transfer function, then it will be open loop transfer function divided by 1 plus whatever the feedback value is multiplied by open loop transfer function. So that in the last lecture video also we have done that, right? So this is what the answer will be, and the simplified will be like this. Now I'm going to solve B25, okay, from chapter 2. Okay, so here there is a control loop given. So this is plus minus, and here you have GCS, which is a controller. So it's controller. Then there is a plant, GP. So GPS. Yeah, and then you had plus here, and CS, and there is a disturbance D. Okay, so this is disturbance. Yeah, so disturbance. Okay, and here comes like this. Okay. So feedback loop, gain 1, you can assume, right? So this is what this is. This is the reference, or S for reference. Okay. What you have to do, it's a you have to find out CS equal to what when both RS and DS are given, are present. Okay. So CS expression of CS equal to 1. So this is a bit different from what we studied, but the idea is to just to demonstrate how you are going to solve this kind of. So in any case, you have to follow how the like flow is, right? So this is the network. It's a network flow you are going to see. It's a block diagram, but have to see how it is going from here, going here, and there it is being added here, and then back feedback loop goes there, like that one. So always good to have just rewrite something, right? So or this will be ES, we can write where ES equal to RS minus CS, right? So this is ES is there. Then here you have GC minus GC times, so this is GC S times ES, and here this is here you have GC S times GP S times ES, right? That's what you have. So this error E, you also call it feed forward transfer function. So which is actually error, basically the reference and the output. Yeah, so this is also known as feed forward transfer function. Okay, so we have so far this one, and then this one becomes DS plus this one. So GC times GP times ES, right? So this is what here, because you are also adding this, so you have like this one. Then it comes back here, and then ES becomes ES equal to RS minus this. So minus this one, the minus DS minus GCS, GPS and ES, all of them. Yeah. Okay. What do you have to find out? It says CS in terms of that. So where is the CS? So CS is, this is what the CS is, right? So we have CS equal to DS plus GC GP times ES, right? That's what it is. And here we are getting ES equal to RS minus CS. This is the CS, like this one. Yeah. Okay. So then what will be the value of? We have to find out CS. Only thing is what is given here is RS, CS, DS, but ES not given. So we have to get rid of ES, and then we will get the solution, right? And for that we are going to use this equation. Right? So you have ES this side also. So we will get the ES from here, and we will put it here, and we will get CS, right? So that's the idea. So from here to here, what you have? 1 plus, and then GCS times GPS multiplied by ES. So ES plus GC times GP, this is ES will be common, is equal to RS minus DS, and hence ES will be equal to RS minus DS divided by 1 plus GCS GPS. So ES equal to RS minus DS divided by 1 plus GCS multiplied by GPS. So this is ES, or the error or feed forward transfer function, and then we use value here, so we will find out CS. So CS will be equal to DS plus GC times GP times ES, where ES equal to RS minus DS divided by 1 plus GCS times GPS. So this is what the solution will be. Here we have DS, GC, GP, RS and all only, and this way this is going to work. So you can also simplify. So let us simplify this. So we can write CS is equal to, now the whole thing is going to multiply by this one, right? So we have DS multiplied by 1 ds multiplied by this gc times gp, but here you have gc times gp minus ds, right? So this will cancel out. So finally what we will have is ds. So if you multiply this with this one, we will have just ds left, and from there this ds will be gone, and ds, and then here it will be plus, and we will have gc times gp times r. Yeah, so divided by, we have the whole thing here, plus 1 plus gcs times gps. So this is what the solution. Again, in your assignment, I may ask question like this one. So there may be a control system like this one, the block diagram and the workflow, the network flow, and then from there you have to find out the expression of CS in terms of all of this. I may give some value of this, or may change something there, you know, maybe include some like in feedback there may be some gain or transfer function here. So this kind of thing can be done. Yeah. Okay, so accordingly you have to find out what is the expression of CS in terms of all of them. So this is the idea of this chapter basically. So summing up things together, find out one as a function of others, and so on. Yeah, so this is what the chapter 2 is. Okay, one thing I need to mention, that in your book you have a state space, okay, method basically. Yeah, so we will not be studying all those, okay, because we like control system is only half of the semester, so that method we will not cover, and vibration part also we did not solve that way, you know. So so whatever method we followed in vibration part, same method we will follow here also. Yeah, so state space, any question having a state space kind of thing, just ignore that, okay? So you don't have to do a state space type thing, okay? So just note that. In this course, you also have some kind of software implementation. So as per your the syllabus, the course template, the MATLAB implementation is given. Okay. Now for MATLAB implementation, all the commands are given in your textbook. So refer to the textbook for that. Yeah. So this is for MATLAB. If you are more comfortable with MATLAB, you can see your textbook. Textbook has all the commands given for the MATLAB. Okay. Okay. What I will do, however, not MATLAB. Okay. So I will do SciLab. Okay. So SciLab is actually like MATLAB only. Okay. And this is open source program, so everybody can install. And given now this lockdown, probably this will be more convenient for students also. So I would prefer that. You know, so the SciLab implementation, that we will be doing it, and you can please install it. So you can install. Yeah. So look for SciLab. SciLab. You may be knowing already. So open source clone of MATLAB actually in a way. But the commands may not be exactly the same. Yes, little bit different. Okay, so but here we will do little bit of SciLab programming. So of course the best way will be to actually I send you the files that you can run. You know, so here we will just do simple commands we will use, and later on I will make some file. I will send you. You can play with it. You can run it. You can see how you can do with that. So it is really nice. You can actually you can see that SciLab or MATLAB already have the controls system commands, and you can generate a lot of things. For example, given transfer function, if the input is step input, what should be the out? How would the output look like? All those kind of things you can do. So it's a really interesting and very useful also. So some of the commands we can, as far as chapter 1 and 2 is concerned, it is all about the transfer function only. Yeah. So transfer function in SciLab, you can make very simple. You can say s equal to %s. Yeah. So that way you are telling that s is a complex I think double slash should work in this case. Double slash means comment basically, so that means telling that s is a complex frequency, right? Frequency. Yes. So S domain. So this is the way of telling that S I am going to use as a symbol, which is used in control systems. So S as in Laplace transform. So you say S equals to %s, and after that you can have transfer function t equal to, you can write is equal to 1 plus s divided by 1 plus 5 s plus 9s square, right? S square here. Okay, so it's not, should not write like this one because it's a programming. So multiplied by s plus 9 multiplied by s, and then to the power 2 like this. Yeah. So okay, and if you say t1, yeah, say this is t1 equal to like this, t1. If you have t1 and enter, then what will you get? You get the answer here. Yeah? So it will give you answer and enter. It will give you answer t1 equal to, it will give like this, 1 plus s, and then it will do like this, 1 plus 5. So it will write like that. Okay, so 9 times s, like that it will write. Or maybe it will show you like this. Maybe it will be here like this. Okay. So that means it will recognize this as a transfer function. Yeah. All these in command line. So command line will look like something like this arrow. Yeah. So this one is actually enter, right? So that's what I'm saying. Enter. Yeah. This is the output. Okay. Okay. Now the similarly you can have T2, right? So you can write T2 is equal to, you may get let us say equal to 1 divided by 1 plus s. You can write like that. Okay. You can also do like T3 is equal to T1 multiplied by T2, yeah, and then you can have T3, or if you write like this one and then enter, yeah. So then you will get the value of T3, right? So you get T3 is equal to, and it will multiply automatically. So you will just get 1, and then you will get like this, and then 1 plus 5s plus 9s square, you get something like this. Yeah, so answer. So this So basically you are just writing now the transfer function. So basically today we understood just how to write a transfer function. Yeah. So based on the transfer function, we will do a lot of things. So transfer function is the most basic thing in control theory, and in MATLAB or in SciLab program. In SciLab program, this is how you do. If for MATLAB equivalent, please see the textbook. Okay, but we will be following the SciLab only for the benefit of all the students, and also these things will be available to you later on also after you graduate. You don't need to. I mean, the SciLab is open source, so you don't have to pay for it. Yeah, so whatever you learn it will be useful later also. So that is all from this chapter 2 and 3. Okay, so chapter 2, 3 is done. Okay, so next week we are going to work on chapter 5. So chapter 4 we are going to skip because this is about some mechanical system is talking about. Okay, and you being the mechanical engineer, you know already, you would know, relate to it, other pneumatic, hydraulic system, all those things. Yeah, so those I leave it on you only. However, I will not ask any question from that chapter. Okay, so for chapter 4, more questions will be asked from here. Yeah, and this also to save time basically. So we focus more on the what is useful. This is just to this talking about some kind of system and some mechanical system, the fluid related system and kind of thing. Yeah, so those things you can relate, you can find out, you can read, and you can understand yourselves. And but in any case, I'm not going to ask any question from chapter 4. So we will do the chapter 5 directly, and chapter 5 is talking about the impulse response, the step response, those kind things you know already. But what is the difference? Difference is this is not mass spring mass system, a spring mass damper system, but it could be any kind of system now. So all kind of system you have studied here. So meaning that it may be just a spring and damper only. There is no mass. In that case, it will be first order system. So how would the first order system behave? So that we did not study earlier. We had mass always. So now we will remove the mass from the spring mass damper system, so that we have just a spring and damper remaining, and then we want to find out how to do the response. If we apply some impulse or a ramp or a step input. Those kind of things we will do. Yeah. So basically same as earlier only, but we are going to learn much more here basically. Okay, so that is all today. See you.